Hi, this is a video about the separation of variables in the time-dependent Schrödinger equation. So if we start by just looking at the time-dependent Schrödinger equation, there are a couple of things to notice. First of all, both the wave function and the potential are functions of both position and time. And secondly, because this is a second-order partial differential equation, it may be possible to solve this using the method of separation of variables. Now, if we consider the very special case when potential energies not depend on time, and so V is merely a function of x position, then the wave function can be written as a product of two functions which depend only on a single variable, t dependent on time and psi dependent on position. Now, if we substitute the product of these two functions back in for our time-dependent wave function, we get this equation here. The important thing to notice here is the fact that psi is a function of purely position. Therefore, it is a constant when differentiated with respect to t. And that means we can pull it out the front of the differential as a constant. Similarly, t is not dependent on position, and so when differentiated with respect to position, is again a constant, and so can be pulled out the front. Now, if we rearrange this equation, we can get an equation, which we have here, where all the time-dependent functions are on one side, and all the position-dependent functions are on the other side of the equation. Now, this means that both sides of the equation must be equal to a constant, in this case, E. And that means we can set up two equations in terms of this constant. So we have these two equations here. Now, both these equations are easily solvable. So the first equation, which is an E in terms of the time-dependent functions, this is just a first-order differential equation. And if we try the trial solution of AE omega t, we find that t is equal to AE minus IE over h bar t. And physically what this represents is the evolution of the wave function with time.
Let's move on now to a time-independent solution of the Schrödinger equation. After a separation of the variables, we ended up with the equation on the top. Now, if you multiply both sides by psi of x, we will end up with the famous time-independent Schrödinger equation that you can see there. To solve this equation, the potential must be specified. We are going to take a very special case, the infinite square well, where the potential is 0 between a region of x between 0 and L, and it is infinite elsewhere. Where the potential is infinite, the wave function psi of x must be 0. So outside the well, the psi of x is just 0, and inside the well, all we have to do is just substitute in Vx equals 0 to the Schrödinger equation, so the term containing the potential just vanishes, and we'll end up with the equation on the left. If we reorder it, only to have the second derivative on the left-hand side, we basically end up with the equation of the simple harmonic motion, for which you know the trial solution, so we can try to substitute in psi of x is b times sine kx plus c times cos kx. And if you calculate the derivatives, the second derivative of this, you can verify that it is indeed a solution. Now we have to specify the boundary conditions. The wave function must be continuous, and we know now the form of the wave function, and we know the boundaries. At psi equals 0, the wave function must equal 0, and the value of the wave function at x equals 0 is just c, so c must be 0. What about L? Well, psi of L must be 0 as well. So psi of L is just b times sine kl. And this implies that k must be n times pi over L, where n is an integer number, so it can take values of 1, 2, 3, because then sine kl will be 0. So for n equals 1, psi of x is just b times sine pi over L times x. Here are the plots of the wave functions for the first three modes for n equals 1, n equals 2, n equals 3. you can see that outside the well the wave function is just 0, and inside the well it has this sinusoidal solution. So to get to the final solution, we know that psi of x and t is just the product of the time-dependent solution and the position-dependent solution. We already solved the time-dependent equation, we already solved the time-independent equation, so all we have to do is just take the product of the two. So the solution for the time-dependent Schrödinger equation in the infinite square well is a times e in the power of minus I times e over h bar t times b times sine n times pi over l x. Thank you for your attention.